Couple of things before you start on our new chapter. Going back last time, I was about 2 weeks ahead of myself. This was a problem we worked in class. It was a fin attached to a wall. We were supposed to determine how much heat's lost by the fin, and we said, let's go to table 3-4 and see if we can make life easy for ourselves by looking at case D, which is an infinitely long fin model. To do that, we had to check ML to see if it was greater than or equal to a certain value. I took the value from chapter 5 for a transient conduction, so backtrack. In your notes, this 0.10 was in there last time when we worked that example. It should have been ML greater than or equal to 2.65. Is it yes? Is it no? The ML value was 0.755. Is that larger than 2.65? No. So we cannot use case D on table 3-4. We have to use case A. So make that correction in your notes, okay, so you have that. Okay, number 2. For homework, I said replace problem 3.142 on the handout with a different problem. Now, that particular problem has a different problem number in different textbook. If you're using the heat and mass transfer textbook, it's problem 3.117. If you're using what's called the heat transfer, Introduction to Heat Transfer textbook, that's problem 3.149. If you're using the Introduction to Heat and Mass Transfer textbook, it's the same problem, but it's called problem 3.117. The picture for that problem looks like this. So just to make sure you're working the right one, it looks like this. It's a tube with baffles in the tube, come out this way, baffles. Okay, this separates, so the flow goes in 4 channels along the tube, 4 separate channels. So if you're confused about that, go to that picture and you'll find it at the end of chapter 3 for homework. One textbook has a problem 3.117, the other one has 3.149. They're the same problem, just renumbered for different textbooks. If you don't have the textbook and you want that problem, take out your cell phone, take a picture after class in my textbook, and you can get it that way. I'll show you exactly which one it is in my textbook. Just a hint for problem 3.51. It's a steam pipe in a power plant. The steam pipe is steel, surrounded by insulation, carrying steam, of course, in a large room where the air temperature is given and the room wall temperatures are given. So you know what's going to happen. The heat goes through the steel, it goes through the insulation, it goes out either to the room walls by radiation or to the room air by convection. So here's your picture of what's happening. Steam in the pipe, T infinity 1. The heat goes through the steel resistance. It goes through the insulation resistance. When it gets to the outside of the insulation, it splits. Some goes to the room air by convection, some goes to the walls of the room by radiation. You don't need to use resistors there because they're difficult to use for radiation, so just show them as this. You know what this is. This is HA delta T. You know what this is, chapter 1. It's epsilon sigma A T surface to the 4th minus T walls to the 4th. So now you write an energy balance on this big black node. The heat that comes in by conduction is carried away by either convection or radiation. The only unknown in that equation is going to be R3, the outside radius of the insulation. Now you can try and solve it analytically. It's a little bit tough because there's a natural log of R3 in here, and there's also R3 on the area for convection and radiation. So it's a little tough. What you can do, if you want to avoid that, is you play the iteration game, the guessing game. Now, first of all, make a reasonable first guess. You know, they tell you that the radius of the steel pipe. They tell you that. So, okay, you're going to add insulation to it. How much? 3 feet? I don't think so. No. Half an inch? I doubt it. No, I don't think so. My first guess is going to be maybe an inch or two. An inch is 2 centimeters. So maybe, I don't know, I'll guess between 2, 4, 5, something like that. I'll put that R3 in that equation. If the left-hand side comes out to be different than the right-hand side, try again. New guess, I guess now R3 is this. So you might put an R3 value in here and get Q1 53, and this side, Q2 plus Q3 48. Say, that didn't work. I'll make a new guess for R3. Okay, now you get Q1 equal 51, and Q2 and Q3 still 48. Say, I'm getting closer. Make a new guess for R3. Usually after about 3 iterations, you get right in there, and the left-hand side's 51.5, right-hand side's 51.4. Stop, you're done. That's close enough. So that's one way to solve that problem by iteration. Guess an R3 and see if left-hand side equals the right-hand side. Okay, any question on those guys then? All right, good. That gets us to chapter 4. Now, we're going to look at 2-dimensional conduction. So here's a solid material, conductivity K, temperature is a function of X and Y. First of all, we want to find the governing partial differential equation. We go back to chapter 2, the heat diffusion equation in rectangular coordinates. Okay, it's 2-dimensional, so get rid of the Z. There's a second partial T with respect to Z. That's 0. We're assuming steady state. Get rid of the partial with respect to T of temperature. Okay, it's gone. There's no generation. Get rid of the Q dot term in chapter 2, heat diffusion equation. It's gone. Assume constant properties. The K comes out the partial sign. You divide through by K. K disappears. We're left with the Laplace equation. So, you can solve this by a number of methods. The first one, maybe analytically, the exact solution. Okay. Maybe numerically. Sure, numerically. We'll do that on probably the last part of Friday and then Monday. And finally, we can get some good intuition and maybe some numbers for Q and temperature from graphical techniques. So 3 possibilities. The analytical technique is described by this. Here is a rectangular plate. The length x direction L, the height in the y direction W. Maybe it's 2 centimeters thick. The thickness is out from the board. Okay, but we're looking at only 2 dimensions, x and y, 2D conduction. Because of the Laplace equation, second partial T with respect to x, we need 2 boundary conditions relating T to x. Second partial T with respect to y, we need 2 boundary conditions relating T to y. Here they are. BC number 1. If I go to y equals 0, the bottom, no matter what the x value is, the temperature is T1. Okay, that's this one. BC number 2. At the top, when y equal W, no matter what x is, T equal T2. Got it. The left-hand side. When x equals 0, for any y value, the temperature is T1. The right-hand side. X equal L. For any y value, the temperature is T1. Okay, there's our 4 boundary conditions. We then solve that equation with those boundary conditions, and we end up with this solution. t as a function of x and y. It's an infinite solution. Okay, so when we solve that, we get a rather complex looking solution. It's sines, hyperbolic sines, infinite series. Yeah, it's rather complex looking. And what solution is that for? That's for a very simple geometry, a rectangular plate. Nothing in the world is much simpler than a rectangular or a square plate. So for a simple geometry, we get a very rather complex solution. You can imagine for a non-simple geometry trying to find the exact analytical solution. Oh yeah, you do that, but not in this course. You take the graduate course in conduction here at Cal Poly, and yeah, you'll do some exact solutions. You'll go through all the blood, sweat, and tears. Oh yeah, they'll make you work, because they want you to see how difficult matters are, and you get the exact analytical solution. In this introduction class, no, we won't do that, okay? This was just an example of how complex things can get. So we'll pretty much do the second two. We'll do graphical today, and we'll do numerical on Friday. Okay, so we're not going to use this. What we're going to do now is we're going to do the graphical technique. I need board space, and this is not going to be used anymore, so we'll get rid of this. Okay, so we'll do graphical first, and then Friday do numerical. Okay, so I'm going to pass this out to you. Okay, so anyway, top of the page, the text page, it says a flux plot is a graphical presentation of the isotherms and adiabats for a solid geometry. Okay, that's what I put on the board here. What is an isotherm? An isotherm is a constant temperature line. What is an adiabat? An adiabat is a heat flow line. So you're constructing a diagram of constant temperature lines and heat flow lines. And then there's some basic rules given there. So let me go ahead and draw an example here. I'm going to take a rectangular plate. And I'm going to assume the top surface is maintained at a constant temperature T1, the left-hand side T2, the right-hand side T2, the bottom at temperature T2. And I'm asked to construct a flux plot for that. Okay, so here's rule number one. Identify lines of symmetry, geometrical and thermal. Lines of symmetry, geometric and thermal. Let's do the geometric. Here's the plate. This is the plate like that plate over there. Here's the plate. If I fold it this way, it's geometrically symmetrical. Okay, so I know one possible line goes through the middle like this. That's geometrically symmetrical. I know that I can take this and fold it about the side, left to right. That middle line is a line of geometric symmetry. Okay, so now don't try and fold it corner to corner. No, that doesn't work. Not symmetrical corner to corner. There they are, the only two. Now find the lines which have thermal symmetry. Okay, take him. Fold him about top to bottom. T2 down here, T2 up here, check. T2 over here, T2 over here, check when I fold it. T2 at the bottom, T1 at the top, nope. This is geometric symmetry, this is a no-go. It's not thermally symmetrical. Fold about here. This side comes up to the top. T2, T1, no, it won't be it. Take this guy here. T2, T2, check. T1, T1, check. T2, T2, check. Yep. This guy is a line of both geometric and thermal symmetry. So get rid of him. He's a no-go. He qualifies. So rule number 2. If you found lines of both geometric and thermally symmetrical about the part, these are adiabats. Okay, we found our first adiabat. What's an adiabat? An adiabat is a heat flow line. Does that make common sense? Of course it does. I know if T1's hot and T2's cold, he's in the middle, he's going to go straight down to the bottom. That makes sense to me. All right, now I'm going to assume that T1 is greater than T2. T1 greater than T2. So in this corner over here, upper left-hand corner, if T1's hot and T2's cold, I think it's going to go right around that corner. Now don't do this. No, that's wrong. Rule 4. Adiabats intersect isothermal boundaries at right angles. That's an adiabat. That's an isotherm. That's an isotherm boundary. That's not a right angle. No, it doesn't go in like that. It goes in like that around the corner. Get rid of that line like that. Now, fill in the rest. Okay, comes out. Right angle. Every time an adiabat intersects an isothermal boundary, it does so at right angles. Because it's symmetrical, you wouldn't have to draw both sides, but I normally do because it gives me a complete feel for the problem, but you wouldn't have to. Okay, now I come out here, and now I start going down that way. Rule number 6. An adiabat bisects an isothermal corner. This is an isothermal corner. T2, T2, bisects, comes in 45 degrees, equal angles. There it is. This guy comes down here, goes into that corner, isothermal corner, bisects it. There's my heat flow lines called adiabats. I call that the adiabats. Now I'm going to draw the constant temperature lines. So I know one is the top surface here. That's T1. That's an isothermal line. I know the two sides in the bottom, T2. That's an isothermal line. It's U-shaped. The top's horizontal. So now I draw the constant temperature lines coming out. They come out of the corner in a fan pattern. They come out, they cross here, they go up there. They come out, they cross here, they go up there. and so on. Yep, now, okay, now here's the rule. Rule 3, inside the solid boundaries, the isotherms and adiabats cross at right angles. Right angle, as best you can draw, you know, it's your sketching skills. Right angle, right angle, right angle. They fan out from the corner. These guys are the adiabats. These guys are the isotherms. Okay, that's the flux plot. That's what it's called, the flux plot. Now we'll take another one. Okay, this one. It's a rectangular portion. And then there's a semicircle. These sides here are adiabatic. This side is also adiabatic. This side's at temperature T2. This side's at temperature T1. Okay, draw the flux plot. Okay, rule number 1. Look for lines of both geometric and thermally symmetrical. No. Okay, no horizontal line qualifies. Vertically, no. Yes, right in the middle. That's a line of both geometric and thermal symmetry. Right angle, right angle. That's my first adiabat, rule 2. Lines of both geometric and thermal symmetry are adiabats. Now, normally, you got a choice. You can draw the isotherms first or the adiabats. That's a choice. Most people have a better intuition about which way heat flows than they do the isotherms. So my intuition tells me let me back up 1 minute. If I do this problem, the guy says, you know what, I made a mistake. I'm sorry about that. Really, T2 was greater than T1. I say, okay, by the way, there's the same picture. The guy says, oh, they're the same? I say, yeah, they're the same. Doesn't matter which is hot and cold. Doesn't matter which is hot and cold. Whatever helps you to visualize it, that's what it amounts to. If you want to say, I'm going to pretend T1's hot and T2's cold, go ahead and say it. Over here. I'm going to pretend T1's hot and T2's cold. Good. I got a feel for that. I think heat's going to flow out of here. It can't get out the sides, so it's going to get out the bottom. Of course. Which way does heat flow? From the top to the bottom. Which way do the adiabats go? From the top to the bottom. Let's take one. Ooh, makes a sharp right turn and goes out the bottom. Sharp right turn and goes out the bottom. Right angle, right angle. Another one. Don't forget, every time an adiabat intersects an isothermal boundary, it does so at right angles. Right angle, 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 right angle. Comes out. Down here, comes out. Down there, comes out. There, comes out. There, comes out. There. Adiabats. They can't get out the sides because, of course, the side's adiabatic. So you don't want to draw a heat flow line going into the sides. Cannot happen. Adiabat, Adiabatic sides means no heat gets out there. Okay, once you've drawn that, now you can draw the isotherms. Okay, I'm going to pretend that T1's 100 and T2 is 0. If this helps you, fine. Okay, 100 T1, 0 T2. Here's the temperature T2, 0 degrees there. Where do I think the line 10 degrees is going to be? This is a line 0. 10, that's 100. You know what I'm going to say. Yeah, right there. Of course, that's the line 10 degrees. But you better realize, here's the rule. Rule 5. Isotherms intersect adiabatic boundaries at right angles. This is an isotherm. It intersects an adiabatic boundary at a right angle. Here's another one, and another one, and another one, and another one. Yep, everywhere they must intersect at right angles. These guys are the isotherms. They bulge out near the top. They bulge out because you end up at the top, it's a semicircle. At the bottom, it's a horizontal line. So they change. Horizontal line, they start to bow up until they get way up here, and then they're a semicircle. That's why I like to draw the heat flow lines first. I have more intuition for that than I do the isotherms. Was there a question? Okay. Okay. Oh, by the way, yeah, we use that rule, so we know that. Okay. Let's see, was there anything else? Oh, okay. It doesn't matter which one's hot and cold. Say T2 is bigger than T1 or vice versa. Doesn't matter. Why do they cross at right angles in the middle? The math tells us they do. Laplace equation. Those two functions cross at right angles. They're normal to each other within the boundaries of the solid. That conclusion comes from that math over there. Okay, so now we'll take this one. All right, let's see. The bottom on this one is adiabatic. And one side is at T2. The other sides are at T1. Okay. Draw the flux plot. Okay. Rule 1, find lines of both geometric and thermal symmetry. There are none. Okay, didn't help me. What am I going to do now? Well, you know, I'm going to assume T2 is bigger than T1. Okay. In a corner where T1 and T2 come together, how does the heat flow? Here we are, T1 on top, T2 on the right, the heat flow line. Almost looks like a quarter circle right there. Okay, fine, draw it. T2 to T1. Got it. Let's take the bottom. Go near the bottom. Heat comes in from T2, it's hot. It's going to go out T1 where it's cold, but it can't get out the bottom. Adiabatic. Guess what it's going to do? Well, you know what it's going to do. Go straight until here, but where it intersects the isothermal boundary, the adiabats intersect at a right angle. Okay. Draw some more. Over here. Draw some more. Uh-oh. I'm approaching an isothermal corner, T1, T1. Down here. I'm approaching an isothermal corner, T2, T2. Guess what it does? Rule says the adiabat bisects the isothermal corner. Okay, there they are. Those are the adiabats. Now, the isotherms. Look at the picture here. When they come out of the corner, the isotherms come out different temperatures in a fan pattern. Fan pattern. They come out and they look like this. When they get to an adiabatic boundary, the rule says, okay, adiabatic boundary, isotherms, right angle. Adiabatic boundary, isotherms, right angle. Everywhere inside, right angle, right angle, right angle, right angle, right angle. There they are. These guys then are the isotherms. So that guy, no symmetry at all. This guy, symmetry. This guy, symmetry. Okay, now, that's drawing the flux plot. Now, we can also say, well, does it help us get the heat flow? Yeah, it can. It depends how much patience you got. You got to construct this thing clearly. Okay, so I think I'll put this here. We don't need this anymore. We'll use that guy. Okay. To get an estimate for Q, we must construct we call curvilinear squares. Okay. So here's a curvilinear square. Here's the adiabat. Here's the isotherms. Of course, they're called curvilinear squares because the sides are curves. Curvilinear square. How do I know when I've drawn a good curvilinear square? When you draw two diagonal lines. If those lines cross at a right angle, you've got, by definition, a good curvilinear square. Curvilinear squares, the diagonals cross at right angles. If you do that with those curvilinear squares, then we can get an estimate for Q. Now, in this equation, I'll mention just a minute, but M equal the number of heat flow lanes N is the number of equal temperature increments and L is the plate thickness. So, but it's only true if you've drawn reasonable curvilinear squares. So here's my picture. Oh, I have to have on my desk a big fat eraser because I know the first time I use a pencil, never a pen, of course. The first time I draw this is not going to be right. So I take my eraser, I say, oh, that line didn't work, I erase it and redo it again. And check for curvilinear squares. Good. 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 I check for curvilinear squares. You're never going to get up in that corner, so don't worry about that corner, okay? Close to that corner. So you check several places. If you're not happy, get out your big eraser, erase it, and try again. Until you say, oh gosh, I worked on it for 10 minutes, I'm tired, it's pretty good, I'm going to stop here. Okay, I understand. Do your best job, though. The closer you get to drawing curvilinear squares, the better that cue will agree with the exact answer. Okay, so for this picture here, number of heat flow lanes. A heat flow lane is like a heat flow highway, heat flow road, whatever you call it. Here's the deal. Heat comes in here at the hot temperature, T1. Where's it go out? Down there at T2. That's a heat flow lane. Heat flow comes in here. Where does it go out? Way over here on the right side. It goes like that. Count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. For that picture, M equal 10. 1, 2, 3, 4, 5, 6. 6 increments. Equal temperature increments. This, don't say lines. Don't count lines. Count increments. 1 increment, 2, 3, 4, 5, 6. I don't know, maybe we'll call the plate thickness, you might call it 2 centimeters, for instance. You might call T1 equals 60 degrees C, T2 equals 0 degrees C. I don't know, you might say K equal 200 watts per meter degree C. You put all that stuff into that cue, and you've got an estimate of how much heat's transferred from the hot surface at 60 to the cold surface at 0. Okay, so we get an estimate of that. Now, there's also a way to get an estimate of temperature. So, this is 0. This is 60. Count the intervals. 1, 2, 3, 4, 5, 6. If that's 0 and that's 60, here's 0, 10, 20, 30, 40, 50, 60. If somebody asks me, what's the temperature in the middle of the plate? Middle of the plate. If I'm a good sketcher, I say, okay, let's count it again. 0, 10, 20, 30. I say 26 degrees right there. Good. Okay, fine. That's an estimate of the temperature in the plate at that point. So it allows you also to get an estimate of the temperature. You say, well, okay, that's good, but you know, so what? Well, the so what's at the bottom of the page here. It says, the graphical approach has 2 important uses. Number 1, it develops an engineering intuition for the temperature field and heat flow in many 2D conduction problems. I don't need to solve the PDE to make that really good drawing. I don't need to get the estimate of 26 degrees here to solve this guy. No. If I can sketch this reasonably, I can give you a good estimate of that temperature or of that heat flow Q. You could be sitting with coffee at a coffee shop on a napkin and sketch that thing out. I don't need Excel to do that. No, you don't. It gives you a good engineering intuitive feel. Number 2, it allows a first estimate of the temperature distribution as a check on the numerical solutions. You program something. It spits out the answers. It tells you the temperature in the middle of the plate is 59 degrees. You say, what? When I sketch it, it was 26. I wonder if my sketching's wrong or if I have a code error in my coding. Oh, you got a code error, believe me. Sometimes you don't know what the computer spits out, if it's accurate or not on a big complex case. You don't know if it's accurate. So maybe by sketching, you can see if your number agrees with what the computer coding spits out. So it has those uses. Very important. Not too mathematical, okay? So it has its uses. If you want the exact answers, you do it numerically. But you can check those answers with a simple sketch like this to see if you're in the right ballpark. Whether I drew 2 more here, and there's 2 more given on the back of the page. Here's a square plate with a hole cut out, a square hole at 45 degree off from the square plate. You can see he checked for, do we have curvilinear squares? Yeah, really good. You can do the whole thing, but since it's symmetrical, you can just take 1/8 of it and then multiply Q by 8 when you're done. So there's a 1/8 of it there. And you can find what M is and what N is, and then you can find it there, the right-hand margin tells you if K is 40, L is 50 centimeters, M is equal to 6, N is equal to 7, T1 is 100, T2 is 30, 19, 20 watts. So you get an estimate of the heat flow. At the bottom of the page is, for instance, a concrete slab with pipes carrying a fluid in the concrete. Concrete slab, pipe carrying fluid in the concrete. You only analyze that one symmetrical piece, the dark shaded piece. 2 people sketched it, left and right. Nobody sketches the same. Typically, their answers for M and N are different. Okay, so first of all, there's no one magic M and N. Different people have different sketching skills. They might get different M and N. The person on the left got M equal 8, N equal 13.25. The person on the right got M equals 7, N 11.5. But when you take the ratio, here it is, M over N, they're both really close, 0.604 and 0.608. But again, depends on how much patience you have when you draw this diagram and how big your eraser is, okay? Because that's what you're going to do. Okay, so any questions on that then? Okay, we'll stop for today. Pick it up on Friday.